Hey, good morning, folks. As you can see by the picture here, I just gave an entire lecture to nobody because I clicked the button on the record button on the video and it only recorded for a fraction of a second and then turned off. So, having rebooted my computer, it's time to do this again. So, forgive my slight eyeball rolling sarcastic thing here. So, at the end of our last video, we learned how to draw a picture to find out what's going on with lenses and mirrors. And I'm going to draw a couple of these optical axes here, and we're going to draw some representative pictures just to remind you how this goes. So, for example, we could have the type of mirror that curves like this. This one has a focal point that's over here, and then we could put an object anywhere we want. There's a arrow or a candle that I could put right there. And for this, we're going to draw ray number 1 and ray number 2. Ray number 1 I draw in blue, and ray number 1 starts life parallel to the optical axis. Remember, there's tons of rays of light coming off of this object, but these two are very predictable and easy to draw. And you only need 2 rays of light to figure out if there's going to be divergence, convergence, or otherwise an image. And so when this one bounces off, ray number 1 bounces off through the focal point. Ray number 2, which I'm going to do here in green, is the opposite of ray number 1. It starts life going through the focal point, or at least in line with the focal point. And then when it hits the mirror or goes through the lens, it turns and goes parallel to the optical axis. Now with these 2 rays of light, they actually cross right here. That means if your eye was over here looking this way, you would see these 2, and they would appear to have come from right there, which means the top of the arrow is right there, the base of the arrow is on the optical axis, and we are looking at a real image that is inverted and looks a bit smaller than the original. Okay, let's do another drawing. This one, let's do the type of lens that is thicker on the edges than it is in the middle. And this has 2 focal points, and they're equidistant on either side. So I'll put them here and here. And we'll put our object out here, although you can put it anywhere you want. And let's go ahead and draw ray number 1, ray number 2. Ray number 1 in this case goes parallel to the optical axis. When it hits the lens, it bends. Now this is a diverging lens, so it bends away from the optical axis, which means it's going to be in line with this focal point over here. So then we do ray number 2, which starts life in line with the focal point. Now we've already used this focal point, so we're going to use this one over here. And we're going to be on our way to that focal point, but we're never going to make it because there's a lens in the way. And when we hit the lens, we have to bend parallel to the optical axis. Now here you're going to put your eyeball on this side and look through the lens at the object, but you're going to see these 2 diverging rays of light, and they appear to have come from back here. So they appear to have come from much closer to the lens, but also much smaller. So this is a virtual image because we had to trace it back. It is upright, and it is smaller again. By the way, real and inverted go together, virtual and upright go together. Okay, let's do one more, and this is the one I'm going to pay most attention to. We're going to have this kind of lens, this convex lens. This is a converging type of lens, and we're going to go 3 centimeters on either side for my focal points, and we're going to go 6 centimeters over here for my object. And now we're going to draw ray number 1 and ray number 2. Ray number 1 starts life parallel to the optical axis. That's not the most parallel ray I've ever drawn, but it should be fine. And then it bends and goes in line with the focal point. This one bends towards the optical axis because this is a converging lens. Then the ray number 2 goes in line with the focal point. Now look, this is barely going to hit my lens here, but it's okay. Even if it doesn't hit the lens, have it turn at the center line of the lens, and then it turns parallel to the optical axis. Now these two really do cross over here, so we have a real image, and the top of the real inverted, and looks roughly the same size. We're going to find out in a second. So this is the kind of drawing you should be able to do. Ray number 1, ray number 2. You should practice with this a little bit. There are some examples in your textbook if you still have that thing. Dang, that's hot coffee. Okay, but good. Starbucks breakfast blend. I begrudgingly like Starbucks. Okay, let me show you something. I'm going to hang on to this here, but I want to draw on this. You may notice if you look at these things here that there are some triangles being formed by these reflections, and that they're gonna have the same angle in different places. So there's a geometrical way to do this. Like, this is a cool little parallelogram of some type, isn't it? If you work out the geometry, you'll see that these things are proportional, but they're proportional as inverses. So this is the lens formula that you can use to calculate these things. 1 over f equals 1 over o plus 1 over I. F stands for the focal length, and it's measured from the lens. Let's make this into from lens or mirror to the focal point. This will be positive for converging type of lenses and mirrors, and it'll be negative for diverging type of lenses or mirrors. Then O is the object distance, and that'll be measured from the lens or mirror to the object. That will be positive for object on left. And since most everybody puts the object on the left, in this drawing I put it to the left side of the lens or mirror, this is almost always going to be positive. And then I is the image distance. And it is, of course, measured from the lens or mirror to the image. And it will be positive for real images and negative for virtual images. Now, real images are on the right side for a lens, because light is supposed to go through a lens, and on the left side for a mirror. Virtual images are on the left side for a lens and on the right side for a mirror. Okay, now this is the formula. There's one more formula that you can use to go along with this, and that is the magnification is minus the image distance over the object distance. And this will tell you whether something is bigger or smaller. Minus means upside down. So if your image distance turns out to be negative, it cancels this and you get a right side up virtual image. But basically, if your image distance is larger than your object distance, your magnification, the absolute value of it, is going to be more than 1, and the image is going to be bigger. So let's use these formulas and let's test one of my drawings here. And I'm going to test this drawing right here because I took care to go ahead and measure these things. The focal distance, whoops, not in inches, in millimeters here, from the 10 millimeter to, so it's 3 centimeters. Okay, so the focal distance is 3 centimeters. This is a converging type of lens, so that is going to be a positive 3 centimeters. My object distance, I made pains to make that 6 centimeters. And we're going to go ahead and solve for the image distance and then see how well I did on my drawing. So let's go ahead and get that out of the way, and let's do this. We're going to say 1 over 3 equals 1 over 6 plus 1 over I. Let's get this to the other side. 1 over 3 minus 1 over 6 equals 1 over I. This is 2 6, this is 1 6, so 2 6 minus 1 6 is 1 6. So 1 6 equals 1 over I, and that means that I must be a positive 6 centimeters. Now, drum roll please, positive means on the right side That is true. And is this indeed 6 centimeters away? It is almost exactly. I get about 5.9, 5.8 centimeters away from the lens here. So I've done a pretty good job drawing this, and this equation tells me it's positive, so it's real. Also, if we put it in the magnification is minus 6 over 6, or minus 1. So it is upside down and the same size. So that's what I get from the equation. So the equation, you can check this out in your book, and there's some things you can do to practice with it. You can get the information from the equation. You can get the information from a drawing. I find that about 2/3 of my students prefer to make the drawing, and about 1/3 prefer to use the equation. Give it a shot. Make a drawing for a lens or a mirror, and then measure your things out and try the equation and see how well you do against the rigorous architectural standard of drawing stuff. If you need any advice on that, come to class and ask me for it. There is one more lecture. In the final lecture, I will share with you using Snell's law 3 things. One is why bodies of water appear to be shallower than they really are. Number 2, and along with that, a thing called total internal reflection. Number 2, the concept of dispersion and how colors are separated, and why a rainbow appears the way it does. And number 3, we're going to talk about polarization of light. So that'll be it. So we have light number 6, light number 7, and that's it for the lecture series.